Oxygen.
it'd be oxygen.
Well, so when something's by itself, it doesn't really matter, right?
I was thinking backwards.
Its oxidation state is, yeah, sodium would be the least electronegative.
Yeah.
And when something's by itself, we don't really need to mess around with it. Its oxidation state is whatever the charge is. So sodium's by itself, has a charge of 0. Excuse me.
Bless you.
Dad sneezes are a real thing. I used to be able to like sneeze in the theater and nobody would notice, and now I can knock myself over half the time. So if we're trying to figure out what the oxidation state is here, it's just 0. It's neutral. It's all by itself. Its oxidation state is going to be 0. In water, now we're looking at a comparison. So now we're looking at what's most electronegative. So oxygen's more electronegative. So closer to the top right corner of the periodic table. I know most of you can't see this, but I can at least point to what corner things are in, right? Still probably helpful, at least for half the class.
General area.
I'm going to kill myself on this today. So oxygen's more electronegative, closer to fluorine. So what charge does oxygen want to have?
-2.
-2.
It needs to gain 2 to be the same as neon, right? So if it was an ion, it would be -2. So we're going to treat it like it actually has access to all those electrons. So that means each hydrogen has to be +1 because there are 2 of them, and we need the total charge to add up to 0 because this is a neutral compound. Right, so the oxidation state on the hydrogen, on each hydrogen is +1, and the oxygen is -2.
So ignore the coefficients at this point?
So ignore the coefficients at this point. The coefficients are there for balancing reasons, so we know what ratio to let these things react in, but they don't really matter for oxidation states. And so if anybody who's ever done a baking soda volcano knows it doesn't really matter if you get your ratio of vinegar to baking soda right, it'll still react. If you want all of it to react, you've got to get the right ratio, but the reaction doesn't change. What's our oxidation state on hydrogen now?
0.
0. Sodium? +1. So when we have 3 elements, if it's an ionic compound, we just break it up into its pieces, right? We know that this is sodium ion, that's a hydroxide ion. Sodium ions are always +1, and the hydroxide as a whole is -1. So what's the oxidation state on the oxygen in hydroxide? Still -2, right? It's still the most electronegative element in there. And now we only have 1 hydrogen, and we need the charges to add up to -1. So it's still +1. We just only have 1 of them now. So, the oxygen really play a role in this reaction?
No.
No. It stayed the same. It changed forms a little bit, but its oxidation state didn't change. So the oxygen is neither the oxidizing agent nor the reducing agent. It's being neither oxidized nor reduced. Sodium went from 0 to +1. So it lost or gained an electron?
It lost.
Lost.
Lost an electron, which means it was oxidized. Leo says her, right? Lose electrons is oxidation,
Yeah, it's reducing.
which would make it the reducing agent.
-8.
So oxygen didn't change, sodium was oxidized, so the hydrogen had to be reduced, right?
Only in hydrogen gas.
Hydrogen goes from +1 to a +1, so that didn't change, so that hydrogen didn't change. But this hydrogen went from +1 to 0, right?
Couldn't we say it that's for plus 2 and plus 4 the other?
There were 2 of them, but they were each individually plus 1. All right, so we can identify where the oxidation is happening, what's the reduction. If we want to identify the oxidizing agent, even though the oxygen is not changing here, the oxygen is not the oxidizing agent. This whole, we basically, you identify one of the reactants on its own as being each agent. So even though the oxygen is not changing, we would say that water as a whole is the oxidizing agent. Even though it's really just the hydrogen part of the oxygen that's doing the oxidizing, those are the 2 chemicals that we would mix for this to happen, would be water and sodium. So that makes sodium the reducing agent, water is the oxidizing agent. And then we could get more granular and say, and the part of the water that is reduced is a hydrogen.
But because they're together, it makes the whole thing.
We would just say that the whole thing is the compound.
Yeah, because you didn't add hydrogen ions, you added
Right.
H2O.
If we did this with an acid, we could say that the hydrogen ions were the oxidizing agent, like the one we did, one of the ones we did in class, right? Zinc, metal plus HCl reacted to make H2 and zinc chloride. And that's not balanced, but that's not the point here. In this case, we could say that the hydrochloric acid is the oxidizing agent. The zinc is the reducing agent, right? Even though it's really just the hydrogen that's that's being reduced. This, we'd say this whole compound is the oxidizing agent.
The most reactive one in there is, no wait, it's,
So
yeah, it'd be
in
zinc.
terms of activities,
Yeah, zinc would be higher than hydrogen.
if this reaction actually happened, right? If it's not a no reaction case. So if it actually happened, it's because we're making something more stable. And another way of saying more stable is less reactive. Everybody has that friend that's very reactive, right? Maybe some people might call them overreactive. Another way of framing that might be that they're less stable.
Unstable.
Maybe not a kind way of phrasing it, but that's one way you can think about activity, reactivity versus stability. They're inverses. When something is more reactive, it's less stable. So if we're making something that's more stable, that means that this was the less reactive of the 2 elements we're dealing with here. Let's see, where is there are my slides. All right, let's do a couple more. We practice oxidation states. And so I'm going to give you a variety of carbon-based compounds. Because just like phosphorus that we ended with the other day, phosphorus can have a variety of different oxidation states it can have that are all at least somewhat stable. Carbon also has a variety of oxidation states. So we've done CO2 before, but we'll practice it again. We've also done methane. We could do formaldehyde, and we probably shouldn't do formic acid. Wait, 1, 2, 3. All right. So if we're trying to assign oxidation state, and again, would normally be used purely in terms of comparing before and after. Assigning oxidation state really has no value on its own. It's always used as a way to compare before and after a reaction happens. And so if CO2, and we'll throw carbonic acid in there too. What's more electronegative?
Oxygen.
Oxygen, so it has to be
The
same as normal, right?
yes.
-2. And there's 2 of them, 2 oxygens, each is -2. So carbon has to be +4. What's more electronegative out of carbon and hydrogen?
Hydrogen.
Carbon.
Oh, yeah.
Remember, hydrogen is our dividing line. Any non-metal is going to be more electronegative than hydrogen, and any metal is less electronegative than hydrogen. Right, so carbon's more electronegative, and how many electrons does it want to get? It needs to gain 4. 1, 2, 3, 4 to get all the way over to neon. It has 4 vacancies in its valence shell. So carbon is going to be -4, which means, and we have 4 hydrogens, so each of them has to be +1. And again, a reminder, since we went fast the other day, hydrogen only has 3 options. It can be -1 if it has an extra electron, it can be 0, or it can be +1. But because it's in that first energy level, it cannot ever have a charge other than one of those 3, -1, 0, +1. So that means hydrogen's actually kind of useful because we know it's limited. We only have 3 options. It's just a matter of what do we pair it with to decide what that is.
How come for CO2 the carbon's a +4, but for CH4 it's a -4?
Because in this case, it's paired with oxygen that's stronger and more electronegative. In this case, it's paired with hydrogen that's less electronegative. Carbon's the middle child.
Yeah, either way it goes, it's either filling or emptying an orbital.
When you put carbon with the baby, carbon can be a bully. When you put carbon with big brother's the bully. And if you have all 3 of them at the same time, we're kind of limited. We have to pick one place to start. So
Oxygen.
who gets their due first, right? Oxygen. So it doesn't matter that we have 3 options here. We can't break it up into ions like we do with ionic compounds, but we can say, well, I know oxygen's stronger than everything else. So oxygen's a -2. So carbon's in the middle. We don't really know what carbon can be until we figure out what carbon can't steal from oxygen. It can steal from baby brother, but baby brother only has 1 electron to give, right? So hydrogen is the least electronegative here, so it has to be what?
+1.
+1, and there are 2 of them.
So C must be 0.
Because you have 2 +1s and a -2. Those add up to 0, and the overall molecule is 0. So whatever the charge is on carbon, it has to make the total charge add up to the overall. So carbon has to be 0, because if it's anything but 0, we would have a charged molecule.
That's
so-
neither filling, emptying, or halfway for an orbital. So how does that make sense?
So this is formaldehyde, which is not a particularly stable molecule. Basically, this is a midpoint. Carbon can be a lot of things. It could, when it has the most energy possible, it has all carbon-carbon bonds and all carbon-hydrogen bonds. When it has the least energy possible, it's fully oxidized and it's CO2. Everything else is going to be somewhere in between those 2 extremes, right? Which is why burning ethane gives off more energy per mole than burning formaldehyde. You can burn formaldehyde, but it has less energy on all the carbon-oxygen bonds because you've already got, so it has less energy because it has fewer carbon-hydrogen bonds. It already has a bunch of carbon-oxygen bonds, so it doesn't have as much energy to give. And when photosynthesis is basically taking this process and going backwards, it's starting here, and you're giving high-energy electrons to carbon to try and get closer to this so that your body can then, or the plant can then use that energy later on, right? So carbon is really interesting when it's really relevant because all of nutrition is either taking CO2 and making sugar with it or taking sugar and making CO2 with it. It just turns out that's a very, very complicated process. How about, let's do carbonic acid over here. Same deal. Start with the big brother. Start with most electronegative. So oxygen has to be -2, and there are 3 of them. What does hydrogen have to be?
+2 and C must be +4.
+2,
+1 twice.
+1 twice.
Yeah, +1 twice.
There we go. Because hydrogen can't have a +2. It only has 1 electron to give.
I meant +1 twice.
I know.
said
I'm just
+2
making the
for some
point.
reason. And C must be +4.
So +2 and -6, we need them to add up to 0, right? So we need another +4 to make it add up to 0. Right, so a reaction where you take CO2 and you turn it into carbonic acid or carbonate doesn't actually change the oxidation state. Carbon's +4 in both cases. It's just changing the form. It's one of those complexation reactions where we're changing how things are arranged, but everything still has access to all the same electrons. Last but not least, formic acid, which is, if you've ever had an ant problem in your house and you squished a whole bunch of ants at the same time, you notice they have a really, really weird smell to them, right? Kind of like weird and sweet smelling, chemically sweet.
I've eaten ants before and they're super sweet.
Yeah, that's actually the formic acid. They actually use formic acid as instead of blood, they have formic acid that acts as one of their oxygen transport molecules. So that's what this molecule smells like, or tastes like, if you have eaten ants. If we're trying to assign oxidation states, again, who gets first dibs? Still oxygen. There's 2 of them, and they're each -2. Now we go to little brother. Hydrogen, still the least electronegative out of the whole bunch. There's 2 of them, and they each have to be +1. So what is the oxidation state on carbon?
+2.
It's got to be a +2. This is going to give us a total of -4. This gives us a total of +2. We need another +2 from carbon in order to make it add up to 0.
So for that one, could you just do carbon as +4 and then hydrogen as 0? With that?
That's not really how it's going to work.
Carbon is the central atom.
Carbon is the central atom, and in terms of when you take organic chemistry or biochemistry, one of the ways you can assign oxidation state is you basically count how many oxygen bonds carbon has. More oxygen bonds means more oxidized.
Okay.
And this molecule is going to have more carbon-oxygen bonds than, where's the one where carbon is? Than formaldehyde. And because carbon really is stronger than hydrogen, so it has to be able to take the electrons from hydrogen.
For sure.
All right, so just as a further note here,
So
as far as these reactions go, this reaction, CO2 to formic acid, is one of the hardest reactions to actually produce at scale reliably in terms of taking solar energy and turning it into something usable. Plants do it relatively well. It's called carbon fixing. When you take CO2 and it's most carbon in its most oxidized state, and we want to reduce it to make it more usable. Getting from CO2 to formic acid to formaldehyde, and then from there we would usually go to methanol, if you could. It'd be that's sort of a holy grail sort of chemical process, because if we could do that, we would be able to just take sunlight and make methanol from it directly without needing to do any fermentation or involve any plants whatsoever. And methanol is a really convenient source of energy because you can burn it really easily, and it's a liquid, stable, transports easily. It's toxic, but not that toxic. So this is actually a big area of research is in carbon fixing. There's basically a dozen different research groups all over the US focused on every one of these reactions. How can we go from here to there, and then how can we take the carbon and then reduce it 2 more electrons? And then how can we take this and go to methanol? So it is, these oxidation states are kind of a weird concept, but they're very useful in terms of being able to judge how much energy things have, just based on looking at the oxidation state of carbon.
So carbon is more oxidized with more oxygens and then less oxidized with more hydrogens?
Correct.
Right on.
Yeah, remember that's where that CO2, where that term oxidized comes from, is because before they even knew what electrons were, they knew that you can take a metal and you can add oxygen to it and it turns into something new. And same with carbon. Right? And that black charcoal that you get when I added the sulfuric acid to the sugar, or when you burn something, is incomplete combustion. You're oxidizing the carbon, but not all the way to CO2. If it happened and it didn't get hot enough, or there wasn't enough oxygen around, you can wind up with it stopping halfway in that process. And that's when you get things like smoke or charcoal or things that are partially burnt, ash.
Why is that kind of carbon bad for you? Like, I love that.
It mostly because you have to get to really high temperatures and really low oxygen contents to do that. And you can wind up making a lot of what are called free radicals, which are unpaired electrons, or peroxide bonds, which is when you have oxygens that have a single bond to another oxygen atom, and those are really unstable and are carcinogenic. So it's basically because the incomplete combustion results in a wide range of things, many of which are can cause mutations and cancer and things like that. So brown, good. Black, not so much. Brown is okay. Brown, when food turns brown, that's the Maillard reaction, which is fairly safe. That's when you get that Maillard reaction, when you have protein reacting with sugar in the presence of heat and usually acid, and you get that's what that nice caramely crisp on texture is on the outside of a well-grilled piece of meat. Or tofu, if that's your preference, is Maillard reaction
And
happening.
caramel.
Or caramel. You need to add milk to make good caramel usually, right?
Yeah.
At least in my opinion, because then you get that creamy texture and that's more of that
And
Maillard.
salt.
That's up to preference. All right, so let's do one more, and it's not going to be oxidation reduction per se. We're going to practice doing some conversions since it's been a while. And balancing. CO2. Let's talk about reaction. Question on CO2 and water. If it's complete combustion, you're going all the way to CO2 and water. And for this class, we're going to assume that all combustion reactions you see are complete combustion. We're not dealing with any incomplete things happening. So propane reacts with oxygen to make CO2 and water. Start by balancing it.
4 on the H2O.
So hold off a second. Just pause, give everybody a second to catch up, and then we'll walk through the logic.
I agree with that.
No way.
And then the second step, if you've already got it balanced, check your work. And then if you still have it balanced, figure out how many moles, actually I'll write it over here. How many moles are in 5.0 pounds of propane?
Pounds, grams.
And I'll also remind you, 453.59 grams is 1 pound. Just the propane. So we have 5 pounds that's just propane. I'm thinking the way you buy it at U-Haul.
How many moles of C3H8?
Mm-hmm. Good call. I'm not sure if I said it or not. This is propane. And it's the only one that you don't know up there, right? You know CO2 and water, and you know oxygen. So that's propane. And you should have a periodic table with you. But if you don't, you say
Is pound to gram exact?
no,
No.
it is not.
What did I say, how many moles of which thing?
Propane. So if you have 5 pounds of propane, how many moles is that?
$298.1.
How much?
298.1.
So that's going to be about 2,500 grams. 2,500. That's about 45. About call it 50 grams per mole. So about 50 moles. Is that what you said?
No.
51. Okay, we'll walk through that in a second.
Yeah, I must have divided here somewhere.
We'll start with balancing though. So, with combustion reactions, I mean, with any reaction, you generally want to leave whatever you can balance by itself, anything that's on its own, save that for last, because we can change the coefficient on oxygen without messing up anything else. So with that in mind, let's just start at the beginning. 3 carbons over here. So we have to have 3 carbons over there, right? And 8 hydrogens over here. We need a total of 8 hydrogens here, and we only have hydrogen in the form of water. So we need to have 4 water molecules. And then everything's balanced but our oxygen. We count up everything over here. We got a total of 10 oxygen atoms, right? So how many O2s do we need to get to 10? 5 of them. Was balancing relevant to answering the second part of the question?
Yes, if that was a different number. No, actually.
Not really. We don't need to have this balance in order to figure out how many moles are in 5 pounds of propane. Because all we need to know how many moles are in 5 pounds of propane is what's the formula of propane, C3H8. And then a periodic table to get these numbers, right?
Yes, is how many are burned, then that number is relevant.
Then we'll, yeah, exactly. That's where we're headed next. So 5 pounds, if we're trying to get to moles, we only really have one way to get to moles at this point, right? It's going through mass. So start by turning 5 pounds into grams. Because then we can go from grams to moles. All right, so 1 pound is 453.59 grams.
You said that was not exact?
That's not exact, although that's plenty of sig figs considering we are starting with 2 sig figs here, but it's always good to pay attention to.
2,267.95.
So if I'm eyeballing this in my head, I'm just going to call that 2,500 instead of, I'm just going to say, call that 500. 5 times 500 is 2,500 if I'm trying to estimate. If you want more number or more sig figs, give me at least 2 sig figs, Jordan.
2,300. Yeah, 2,300, right?
And then we want to go grams to moles. So we need the molecular weight here. 3 carbons plus 8 hydrogens, so the molecular mass is 3 times 12.011 grams per mole, plus 8 times 1.008 grams per mole.
44.097. Oh, I know, it would be,
0962. So And really, we're not going to keep all those sig figs anyway, right? Because we went to the thousands place for each of these individually before we multiplied, so we're still only going to go to the thousands place as far as sig figs go here. Remember, these are not exact numbers, these are measured. So if we want, and remember, it's a combined unit. It's been a while since we've done this, but anytime we've got a combined unit, that is a conversion, right? So we can say 44.096 grams is 1 mole of C3H8. Grams cancel out. We're left in moles. And we only need 2 sig figs. We only started with 2 sig figs. If you didn't round in the middle, you might have be off by 1 here, that's fine. All right, so that should be review, right? It's been a while, but should look familiar. Hopefully that feels pretty comfortable, even if you needed to take a second to remember how to do it. So then the question begins, okay, well, how do we use that? We have a way to get from mass to how many moles we have of something. How do we use a reaction to figure out how many moles of product we could make? So the rest of this lecture is going to be practicing saying, okay, well, let's say I've got 51 moles of propane. How much CO2 can that make? Because that's the whole purpose. This is where balancing the reaction comes in.
You have 3 moles of CO2.
So because for every time we burn 1 mole of propane, it makes, say it again?
3 moles of CO2.
3 moles of CO2, right? So if we're going to burn 51 moles of propane, we would want to multiply by 3, right? The way that we show our work for that, just because it's not always going to be as convenient in numbers like this, is we can say 51 moles of C3H8, and these coefficients become a conversion. Because this is a balanced reaction, right? Anytime 1 mole of this burns, it makes 3 moles of CO2. We can say that those two numbers are equal to each other. We can say 1 mole of C3H8 burned is 3 moles of CO2 made. And so, like I said, in this case, if just by looking at the coefficients, 1 to 3, you might be able to look at that and say, oh, well, I'm just going to multiply by 3. But you're going to want to show your work for these because it's not always going to be nice, neat numbers like that. They'll always be whole numbers at least, which is nice. Is this an exact conversion?
Yes.
Why?
Because it's whole numbers.
Because it's whole numbers? Because we couldn't be off by a tenth, right? When we balanced it, we were counting atoms on each side, right?
Yeah.
So really, it's a counting number, which means it's exact. We couldn't be off by a tenth of a carbon. The same way that counting the number of protons in a nucleus is an exact number, right? Because there's no way you're off by a tenth of a proton. You can only have whole numbers of protons. Jen?
So the answer is 153 moles of CO2 made, but as far as sig figs go, because we're dealing with
It's
two
the exact
numbers,
number.
and then only, well, no, we're not using the tiny numbers, but only 2 numbers.
So we would technically we'd need to round off a sig fig here.
Roughly
Right.
150.
Bingo. 1.5 times 10 to the 2, or 150 plus or minus 10. And the reason that the sig figs aren't really matching up is because I'm kind of going rogue here. I don't have my slide in front of me, so I'm making up questions as we go. If I'd given us more sig figs at the beginning, then we could have kept 3 sig figs here.
So
Right, but go ahead.
so the oxygen on the left side doesn't affect how much of something you're making, because that's what doesn't make sense to me. So you're taking the hydrogen and you're saying that it just makes CO2, but
Right.
you need that oxygen in order to make that CO2.
Right. So what are we assuming?
you
By
have
doing
enough
this.
oxygen,
We have enough oxygen.
or excess oxygen.
So the chemical term or the official term would be we have excess oxygen. Basically, it means we're not going to run out of oxygen. We're assuming that we don't know what the conditions are, but if we don't know anything about it, we're assuming that there's enough.
Okay, so could you switch this whole program around saying to like how much propane or how much water can you produce from
Yeah.
use of propane?
We can make this be whatever ratio we want to answer the question. If I said how much oxygen is needed to burn 51 moles of propane, we would just switch up this step, right? So let's say that, let's go that direction. Let's say, okay, I'm writing it this way carefully because this is the way that I write it on tests, is how many moles of oxygen do we need? Well, if we're just comparing these two, then it doesn't matter anything about the right-hand side. Once we know it's balanced, all we care about are what we have and what we're trying to figure out. So, and that means that instead of being a 3-to-1 ratio, because we're not talking about CO2, 5 for every 1 mole of propane, it's 5 moles of oxygen needed, or used, or reacted. Anything that's on the left-hand side of this equation is going to get used up, right? And anything on the right-hand side is being made. So we can put whatever descriptive terms we want here to make it make sense given the way the question's asked. But whatever's on the left is being used, whatever's on the right is being made. This step right here, that's all stoichiometry is. A big scary word that I led into the other day. All it is the idea that we can use a balanced reaction to make conversions. And that allows us to compare moles of one thing to moles of another. That's literally the only step that is stoichiometry, is that step. Okay? And just because I always do a food analogy to sort of introduce this topic, we're going to rewind for a second. We're going to reestablish this concept one more time using a food analogy. But this is actually a convenient place to stop for now. So we're a little bit earlier than our normal break time. So let's take a 10-minute break. Let's come back at 5 till. And then we're going to go and redo this with hamburgers. I'm open to suggesting as to what kind of food we should talk about, but it's right after lunchtime, so let's not get too hungry. All right, 5 till. We'll resume.
This whole thing we were just doing right here, Sean, this was just theoretical yield, right?
Yeah.
Right on.
And this would be, the amount of reagent used.
Right, for 51 sandwiches, you need 3 pieces of bread and 8
Right.
slices of ham.
Exactly.
Whatever it is.
Yeah. Yeah.
Oh, yeah, those sandwiches.
I can speak on that.
Yeah. But I looked at the lab and I said,
On a scale of 1 to probably a host, how do you feel about $400 rate tax and 5 rate to make you?
That's an interesting one. In terms of like therapeutic value, probably not a whole lot unless if you have anxiety problems and that's part of like a calming mechanism that you've taught yourself is part of.
It could, my fiance thinks I could implement it.
So the reason that there might be something to that is like, if you've ever put a baby to sleep that's upset, putting a little rhythmic motion can help them calm down, but I don't know how much of that is, the motion of somebody holding them and how much of that is the motion itself. But it's as, and again, if you coupled it with something therapeutic as far as like going to therapy, like, okay, I know these are my tools. When I feel an anxiety attack coming on, I'm gonna go meditate, or I'm gonna do this or that. If that can be part of that, you can kind of train your brain to say, okay, when I feel that rhythmic pulsing on my wrist, that's a key that, hey, I need to remember and calm myself down. More of a mindfulness technique than anything else. I would not put much stock into it past that necessarily, but I also have not read up on that. That's totally me shooting from the hip. And sometimes I get surprised by stuff like that.
It's all in the sheets.
Sean, are we getting our polyatomic tests back today?
No, I got buried yesterday, and I played around in lab instead of trading. And then I have to move out of my office by the end of finals week. So all my spare time went to doing that. I should have graded, but the grades will be up. If not today, then sometime tomorrow probably, and I'll give them back when we get back from Thanksgiving break.
Oh, we don't have class on Tuesday?
We do not have class on Tuesday.
The school,
The whole school is closed down for all of next week. So I'm going to give you an ICA. Since you didn't have an ICA this week, you'll have an ICA over the break, and it's just going to be practice with stoichiometry. I'm going to give you, it's like 4 or 5 reactions, it's like balance. Figure out how much product you could make. How many moles of reactant did you start with? How many grams of product can you make? Just, repetitive gets you used to that process, because that's the last big concept we have for this quarter is stoichiometry.
Are you gonna throw the key up on there after, more towards the end of the week?
Likely. I think I still have a key saved.
Well, and then for the quizzes, because we were supposed to do quiz 6, and now it's due this weekend, right?
It'll be, so yeah, we'll talk a little bit about that too. So, and when I will scale back the ICA, because the quiz is basically going to be a bunch of really facet. Balance this reaction. That's one of your 4 questions. Balance this reaction. So it'll be a really quick review to make sure that everybody's understanding things properly, and like how many moles of product can you make from this. So it'll be similar to what you do on the ICA, but with the right answer. I think I have it set up so the right answer. It'll give you the right answer so you can check your work in real time. And so that we're still on that same category, that same path of as many quiz assignments as possible, so that people, one bad quiz does the same deal.
Well, was there a quiz 7 that was also going to be used?
It's the one that I was just talking about.
Oh.
So I just pushed it back. We're missed one lecture that would have made the difference for whether or not we could do that one last week. But I forgot to change the deadline on it before.
And then how about the following weekend?
We will not have an extra quiz now. So one quiz due on Sunday, due this coming Sunday, and then a homework assignment.
And next Thursday is closed down as well?
That's Thanksgiving.
Cool.
So yes.
Completely off next week.
We're completely off next week. I will be out of the state.
So then the
Good
ICA is
Probably on Tuesday, so that give you guys a chance to ask questions about anything you still have questions about, or you turn it in. You're the one looking at the calendar, but yeah, so that would make it a week from this coming Tuesday.
Because the ICA and the lab that we just did.
So the nomenclature ICA is due today. The lab that we did will be due the same day. We do a week from Tuesday. Just so you can ask questions if you have more questions about that. Okay, so I'll change that. This is what happens when I import last year's Canvas shell, is it auto updates all of the dates, and until I go in and change them by hand, which I don't do until I know where we are. So I'll fix that. Thanks for letting me know.
Yours says it where if you get 50% on every homework, you can choose to take the final.
I'm never able.
Yeah, you just have to do half of all the homeworks and then you can choose, so. Not a lot. As long as like touch the 6 and basically done. They just keep it. It's not calculus. It's like
I'm not gonna mess with it right now.
It's a can of worms.
It is. I mean, I know I have a pretty good idea of what the problem is. This thing is not directly attached to the ground, it's just sitting on top of an outlet that's in the floor.
Oh, right.
And this whole thing has one power cord that goes to that outlet, and something came loose somewhere, but I can't see it from in here,
Yeah, you gotta pick the whole thing up.
right? And it's just not worth it.
Kelly, the one, that one.
Nice. All right, we'll ease back into it because there's still a few people coming back in. Unless anybody has any, I think hamburgers is a good way to do this because hamburgers have discrete countable pieces, right? I've done tacos before, but then it's like a scoop of carne asada, and that's harder to quantify. So hamburgers make a lot of sense because it's a discrete number of objects. So we're trying to write a chemical reaction. Well, really, we're writing a recipe in the form of a chemical reaction. We're making one cheeseburger. What do we need for a cheeseburger?
Cheese.
Cheese.
Buns.
We're going to call the bun bread so we can quantify the top and bottom. Chlorine, bromine. And we need a patty. Let's just keep it. I'll do one more thing. Pick one more ingredient. What do we need on there? Pickles. Oh, I don't like that. I'm not a pickle person. I would have gone tomato myself, but
Lettuce, fig jam if you want to get really weird.
Yes.
now you're sounding like the hot dog stand at a Mariners game. The people get weird in Seattle with their toppings for hot dogs. Cream cheese is one of the big hits.
What?
It is. I will put cream cheese on my hot dog because it's very tasty, but it's also odd.
All right, guys, something interesting. There's actually a body that decides what can and can't put on the hot dog, the National Sausage thing.
It's actually a very polarizing debate, and so I want everybody to consider real quick. Is a hot dog a sandwich?
Not by the legal
There's
definition.
actually a study that shows that everything is either a sandwich, a soup, or a salad. There's actually like a site that shows that every food you could try to come up with If it's more water-based, it's a soup, and like they go through them, and every single one of them is less.
So
But
like
that's
spaghetti's
some-
a salad.
Yeah, exactly.
Spaghetti's
Like
a
the weirdest,
salad.
weirdest thing.
Macaroni salad is a salad, but why not spaghetti?
So we can do an alignment chart for hot dogs.
Oh my God.
Sandwiches. Sandwich alignment chart is you can be structural chaotic, structural neutral, and structural lawful.
A taco's not a sandwich.
And then you can have ingredients on the same axis, right? So you can say, okay, well, a sandwich has to be savory ingredients, and it has to be between two pieces of bread. Is your definition of a sandwich? But you know, do the pieces of bread have to be connected?
What about
Is a
lettuce?
taco a sandwich?
Does it have bread? Is it just
Yeah, right? So it's one of those things where you got to figure out where you stand here. Look up the sandwich alignment chart and see where you fit. I'm kind of the ingredient and structural anarchy and ice cream. A choco taco is a sandwich sort of approach.
In-N-Out will give you a hot hamburger sandwich with lettuce as the buns if you ask for low carb burger. So the lettuce is the bun.
So yeah, if you're saying that anything can be a bun, it just needs a wrapping, then lettuce can be a bun. So where does that fit? Anyway,
It's a hamburger sandwich. A burrito would be a salad.
Okay, guys, I looked it up. So we're looking at the legal definition.
according to the sausage festival.
No, actually, the USDA and the
USDA,
FDA. If a ham and cheese sandwich on one slice of bread would be the responsibility of the USDA, which is also the responsibility of hot dogs. But if you have two pieces of bread, it's the responsibility of the FDA.
Huh. There you go. There's a legal definition. If it's two, then we're still back where we started. Is a hot dog bun one piece of bread or two?
Someone needed a job.
It's one. It's connected.
But anyway,
Someone needed a job.
let's bring it back. I know I started us on that tangent, but let's bring it back.
Hey guys, water wet? No, no.
It's not.
I'm not gonna start that debate.
How do we balance this? Is this balanced?
You need two pieces of
Subject to
bread.
interpretation.
Subject to interpretation. So let's decide on a standard for this class, for this problem.
2 pieces of
Two patties.
2 pieces of bread. We're counting top and bottom.
Half of it.
We're doing a double, or how many pickles? Probably want like 3 slices of pickles, right?
Or-
Yeah.
0 pickles.
0 pickles for me. And if it doesn't have 2 pieces of cheese, then it's just not worth it.
It's not a cheeseburger at that point.
It's a ham.
Right. You need at least as much cheese as pickle,
You need at
as
least,
far as like volume, right?
you need at least 1 patty to make a burger.
So I guess might as well.
There it is.
It's a grilled cheese sandwich.
And then we'll just, in the interest of keeping this simple, we've already lost that thread, but we'll just say it's 1 patty. Because we're not talking about a double cheese, a single cheeseburger, a junior bacon cheese.
So if you do 2 patties.
Oh man, we've gotta add the caramelized onions.
Right. So we could get crazy with this, but this is already 4 ingredients. It's already more complicated than most chemical reactions, right?
Right. Yeah.
All a chemical reaction really is a recipe. It tells you what to mix together and in what ratio in order to get certain products. So if I said, let's see, I had the numbers already picked out here. You go to the grocery store and you buy a package that has 16 slices of bread, because we're heathens and we're just going to use bread instead of buns, just for the sake of this problem. I do not endorse that behavior.
Well, that's what they made the first hamburgers with.
Right? If we have 16 slices of bread and 10 patties, how many hamburgers can we make?
8. Make 8 full cheese.
If we want to show our work, so we can see, because these are physical objects, we can picture that in our head, right? If we have 16 pieces of bread, and we'll use, instead of moles, we'll say pieces, and 10 pieces of patty. If we want to show our work here, we could say, okay, well, if I use all 10 patties, out of habit, I tried to correct that to lead. All 10 patties, every 1 patty, and then platinum, can make how many cheeseburgers?
One patty makes one.
10.
One patty makes one cheeseburger.
Oh, right.
Man, using these non-standard symbols is really messing with me today.
Yeah.
So if we used all of those, we could make 10 cheeseburgers. If we use all of our bread, we can only make 8, because even though we start with more pieces of bread,
Easier with bread.
yeah. Every 2 pieces of bread is 1 cheeseburger. So we would have to divide by 2 to cancel out pieces of bread and be left in cheeseburgers. We can't make both of those amounts, and we can't make 18. We're never going to take these and add them together, right? It seems silly to even say that right now, but sometimes people will try to do that when these problems. Because there's something about when we switch this to being chemicals instead of being ingredients, freaks people out. It becomes way more abstract, even though the concepts are the same. We would never say, well, therefore I can make 18 cheeseburgers because I have enough patties to make 10 and I have enough bread to make 8, therefore I can make 18. That's ludicrous, right? So don't do that with your chemicals either. The right answer is the one is smaller, right? Because that tells us what's running out first. We have enough bread to make 8 cheeseburgers, therefore we can make 8 cheeseburgers.
That's a theoretical yield.
That's what we call a theoretical yield. So assuming everything goes properly, meaning I don't drop a patty on the ground.
Well, you still have a patty.
Theoretical yield is this is how much we could make if everything went perfectly. Based on what we
Excess of
started.
everything else, right?
No, this is, oh, sorry, yes, assuming we have excess of everything else.
In this case, we have excess of cheese and pickles.
We have a whole jar of pickles and we have, you know, I don't know, all the cheese. Yeah. Now we're living in fantasy land, right? All the cheese.
All of it.
That's all there is to stoichiometry. It's just we're going to replace these with chemicals. If it's balanced and we're in moles, this doesn't work if we're not in moles, right? Because if I told you we had 20 pounds of bread, how many cheeseburgers could we make? That depends on a lot of things.
All right,
All of a
what's the
sudden, we need to take it and get to pieces of bread again, which is equivalent to getting to moles. So we balanced it in terms of pieces or in terms of moles. Therefore, our stoichiometry only works in terms of moles. Right? So the rest of this part of the course is going to be basically, here's a reaction, here's some starting material or some ending material. How much did we start with? Or how much could we make? And the trickiest part is going to be, how do I get to moles sometimes? If I give you a mass, we know how to get from a mass to moles, right? But we'll learn some other ways. If I give you a concentration and a volume of a solution, we can get to moles. Turns out when we get to gases, we can say, okay, if we have this many liters of gas and it's at this pressure and this temperature, how many moles is that? But it's always going to come back to get it to moles, and then we can do stoichiometry with it. Okay? So let's, just so that we're going to really cement it in everybody's head that just because it's chemicals doesn't mean we need to freak out. We'll do the same exact thing with a chemical reaction.
Because the only difference between like this example that you gave us in chemical is that you'd see the elements on both sides of the reaction, right?
Right. Where basically we know in our head that a cheeseburger has all of those pieces as part of it, right? We could write the molecular formula for our cheeseburger would be PaCH3Br2PI3. We redefine that, say that's a cheeseburger. Now it's balanced, right? I'll remember that for next time because I like putting the subscripts with our fake elements. That's kind of fun. Chemistry humor. So here's a reaction. Aluminum plus bromine gas reacts to form aluminum bromide.
2, 3, 2.
We need to balance it, right?
That's the balancing.
We can't do any stoichiometry unless it's balanced. That's like trying to do our recipe without knowing the proportions. You're going to get something, some sort of abomination with only one piece of bread if you do that, right?
Well, you get an open face.
An open
same
face.
way.
Which is beside the point, not what we want. So we have 2 bromines here and 3 there. So this is going to have to be an even number, right? Because we can only deal in even numbers here. So make it an even number. Now we've got a total of 6 bromines on the right-hand side. So we need 6 bromines on the left. Bromines are good. Finish up with aluminum. 2, 3, 2.
Just 1.75, right? 1 to 1.
So if it's 1 to 1, that's a 2 to 2 ratio.
1 to 1.
Mathematically, and so when you're showing your work, especially when you're getting used to this, you still might want to show that step, even though mathematically nothing's going to change. If we want to know how much product we can make, well, every time we use 2 moles of aluminum, we make 2 moles product. So times 2 divided by 2, mathematically we could reduce that to make it 1/1. But really what's most important is that we're showing moles cancels out moles. Nothing tricky about it, right? We're not dealing in whole numbers anymore because we can have, 1/100th of a mole. And we're dealing with chemicals, which are more abstract to our brain than physical ingredients that we have some knowledge of. But the process is identical. This is literally one of the toughest concepts for people to get sometimes. And this is why we spent so much time on conversions earlier, is because of this concept. People struggle with this, and they shouldn't, because if you can do the ICA problems we were doing earlier, you can definitely do this. The math is easy. And the concepts are not even that hard. But something about me giving you a blank piece of paper and saying, what's the theoretical yield for this reaction? Everybody, loses their mind.
Intimidating vocabulary.
It's exactly, that's all it is. It's just vocabulary. All right. If I said, how much bromine do we need? In order for all of our aluminum to react? Well, let's start the same way. If all of our aluminum reacts, every time 2 moles of aluminum reacts, 3 moles of bromine react.
2.625. 2.63.
We could say used, we could say needed, we could say reacted. What's important is that from the balanced reaction is where we pulled these numbers, right? And that we're canceling out moles of one thing and ending in moles of something else from the balanced reaction. If you don't have the balanced reaction, or if I ask you about something that's not in the reaction, you're going to need more information. Right, so this only works for within one chemical reaction, and it has to be balanced before you start. All right. Let's go back to our question here, and let's say that we can say something like, okay, 1 patty. All right, so let's start by framing the question. If I buy 4 pounds of meat and
Patty's quarter pound.
And 2 pounds of pickles. How many, assuming we have enough of everything else, how many cheeseburgers can I make?
How much does one pickle weigh? Or one
We've
patty?
got to get to pickles, right? Because our recipe says 3 pieces of pickle to make 1 cheeseburger, and 1 patty to make 1 cheeseburger. So I like your assumption that we say, okay, well, 0.25 pounds. A quarter pounder is a pretty standard patty size. And for pickles, we can say, I mean, think about what's a pound of pickles?
Like a jar?
A jar, so what, maybe call it 56.
That's a lot. Those are maybe small pickles. The small ones.
I don't know, I don't eat pickles.
There's 56 pickles.
These are big pickles. Here.
Small pickles. There's a lot of them.
I'm thinking about the jar with the brine in it too. The brine takes up a lot of the weight.
Jesus.
How many cheeseburgers can we make? Well, first thing we got to do is get to how many patties do we have. So 4 pounds,
We got 16.
and every 1 pound, or sorry, we had it the other way around. 0.25 pounds is 1 patty. Call it 2 sig pigs.
$164. No, wait.
That's 16.
112.
I'm sorry. I did 41 for some reason.
41, that's not even all that close.
16 pounds. I mean, 16. God, I can't speak today.
This is why we show our work, right? So pause, take a deep breath.
16 pounds. Oh, that's why I saw the L as a 1 for some reason.
So I try to be careful with my
L's.
L's as well, just like I asked you to be. Pounds are just weird. So for every 1 pound is 56 pickles. So 112, which, since we're dealing with whole numbers, I'm fudging on sig figs, so don't take this as a good example for sig figs. So now how many cheeseburgers can we make? Now that we're
16.
in pieces, we can say, well, 1 patty makes 1 cheeseburger. So 1-to-1 ratio, so 16. If we do the same thing for pickles, we say, okay, well, for every 3 pickles is 1 cheeseburger. That's not going to be an even number, so it's going to be what?
37.333.
37.
So the lowest number is what you choose.
We have enough pickles to make 37 hamburgers, but only enough patties for 16 hamburgers. So I'm falling into my California roots, and a hamburger is by definition a cheeseburger in my world. It's funny, if you go to the Midwest, that's not assumed. If you say a hamburger, you'll get a hamburger with no cheese on it, and no veggies usually. What they call a California burger is a burger with cheese and lettuce and tomato on it, which is weird. My brother-in-law came out here and he ordered when he was like 20, and he ordered a California burger, and it came with like bacon and avocado and chipotle aioli. And it's, what is this? So, does anything about this change just because we're dealing with chemicals? Spoiler alert. The answer is going to be no when I ask that question, right? Conceptually, it's the exact same thing. We just are going grams to moles instead of pounds to patties. Okay?
Is it the texture? Is it the brine? What's going on? Do you eat
I think it's
anything that-
cucumbers. I like lots of pickles, just not pickled cucumbers. Give me pickled peppers, pickled carrots, pickled baby corn.
Pickled eggs.
Pickled Brussels sprouts would be delicious.
Another part of the country where you could walk into any gas station and find a giant thing of pickled eggs.
A big old
Oh,
jar.
I've never done pickled eggs.
They're delicious.
It depends
Pump
on what
the
you
brakes
pickle
on
them in. I like them pickled in beet juice.
So actually, good PSA, and a plug for one of my favorite places in town, Sedelis, makes their own pickles in-house. It's a brewery that's right over by Safeway. Their pickle jar, it's phenomenal. They do things like they'll have like broccoli that's pickled, and they do a ferment, not a brine. And so they'll do a broccoli that they do with ghost peppers in it, so you get this really spicy, briny broccoli. It's delightful. My kids will plow through a pickle jar, except for the ghost pepper ones. I have to grab the Brussels sprouts early, or I don't get to taste them. All right. Let's do some more practice, and we'll introduce some more vocab. All right, here's the reaction. We're going to do acetylene. Acetylene burning with oxygen. It's a combustion reaction, so it makes CO2 and H2O. We've seen this before, right? All that changes is what's burning. If you have five kilograms of acetylene, what's your theoretical yield in terms of grams of CO2? Right, so start by balancing. Guess I may as well leave that there since you're going to need it in a second. I start by balancing carbons and then hydrogens.
2542.
We wind up with an issue, right? Because we have 5 oxygens over here and we can't have an even number, or an odd number, excuse me. So if everything's balanced except for the oxygens, then all we have to do is multiply everything we already did by 2. Now there's 4 carbons, and we have enough hydrogens to make 2 waters. And now we can just fix the oxygen. So now we've got a total of 10 oxygens on the right. So we need 10 oxygens on the left. If you're ever balancing a reaction and you get all of your coefficients are even, then you didn't do it right. You might be right, but you need to divide everything by 2 because we want the lowest whole number ratio. So if I got 4, 10, 8, 4, everything's even, I know I can divide all those coefficients by 2 and everything will still be balanced. And everything will still be a whole number. In this case, we're close, but this is a 5. The fact that this is a 5 tells us we can't do that. So if we want to take 5 kilograms of acetylene and we want to know how many grams of CO2 we can make, this is called a mass-to-mass stoichiometry problem, but it's really just a series of steps. You still got to go from kilograms to moles, and then you can go moles of acetylene to moles of CO2, and then you can go moles of CO2 to grams of CO2. Right, so first things first, let's get this in moles. We're going to break it up into steps so we can see what's going on. 5 kilograms. Don't mix up your conversion. A gram is smaller than a kilogram, right?
Yes.
I didn't like how many of those type of corrections I had to make on the midterm. with people mixing up meters and kilometers or meters and centimeters. So remember, gram is smaller than a kilogram. Big number goes on top. And then we want the atomic mass here, or the molecular mass. So 2 carbons and 2 hydrogens gives us a mass of 26.04. 0378. 04 is good enough for us. We only need 3 sig figs. Right, we just got that by adding up 2 carbons plus 2 hydrogens from their masses on the periodic table. So we get something like 200?
192. Yeah, it would be 200. For,
No, 3 sig figs.
Oh yeah, 192.
Moles of acetylene.
384 moles of CO2.
So it can be helpful to, once you do that step, rewrite it up here to keep everything organized. We're still trying to get to grams of CO2, so we need to get to moles of CO2 first. Dylan? Okay. So now if we want to go moles to moles, we can use our balanced reaction. This is our stoichiometry step. 192 moles of C2H2. And for every 2 moles of C2H2, we get 4 moles of CO2. Again, you can reduce this, but there's absolutely no need. Might as well just keep it the same coefficients as you have up here so you don't confuse yourself.
Nailed it.
I can still do arithmetic sometimes. So
That's not our answer.
that's what? Not our answer, not yet. We're close though, right? Now we're in moles of CO2, so now we're done with stoichiometry. Now the rest of this doesn't even matter now at this point. All we need to do is take moles of CO2, put it in grams. So molecular weight of CO2 this time.
44.009.
44.009 grams is 1 mole of CO2.
Uh, 16,900 grams. So 1.69 to 10 to the power of 4.
Or 16.9 kilograms. I asked for it in grams, but just to give us some context, since we started with 5 kilograms, now we have 16.9 kilograms.
For every, we'll get that out of 5 kilograms.
5 kilograms, if we burn all 5 kilograms of acetylene, it'll turn into 16.9 kilograms of CO2.
So let's just say if you were to add another step of that, like let's say you also wanted to know the weight of the oxygen on the left side, would you then use the weight that we just figured out from the right to figure out the left, or no?
So basically, we would, everything from here forward would be different.
Okay.
So we just do it as a separate calculation. This is not changing just because we're changing what we're asking about when the other compounds.
Mhm.
But the rest of this is not relevant to anything to do with oxygen.
So 4 moles of CO2 doesn't equal 5 moles of oxygen?
It does, it's just answering a different question.
Oh, okay.
We could reset from here, and then we would start by saying, okay, well, 2 moles, 5 moles of O2.
Okay.
Yeah, we could figure out how many moles of water as well.
We can figure out how many moles, how many grams of water as well.
It's just not what we're being asked.
Right. Answer the question that's asked, not the question that you want to answer. Did we just violate conservation of mass? We started with 5 kilograms of acetylene and we made 17 kilograms of CO2.
How many kilograms of O2 went in?
Yeah, we rearranged it. The rest of the mass had to come from the oxygen. Right, the oxygen in here is where the rest of the mass is coming from, so no. So conservation of mass means that the total on the left side has to equal the total mass on the right side, not that we have the same number of molecules or that they're going to be attached to the same atoms, right?
Could we say 17 minus 5, and that's like the mass of the
Close, except that you can't forget about the water.
Oh.
We would need to total up all of the mass on the right-hand side, and then we could do a subtraction, because we could, if we would wanted to find the mass of oxygen, we could either go about it by taking 192, figuring out moles of oxygen, and then going moles of oxygen to grams of oxygen. Or we could also say, okay, well, these two total masses have to add up to these two total masses. And that's a good way to think about it, because that's one of our easy algebra equations to write for word problems is all the pieces have to add up to the total, right? So that is something that will show up on word problems in ICAs, where I say, well, you started with a total mass of this, 10% of it is oxygen and the rest is acetylene. How much product can you make? And so then you would have to work your way through it like that. I can get tricky with how to get to moles, but once you get to moles, the rest is easy. And actually, that was the next question on here is how many grams of O2 are required to burn all of the acetylene?
We're jumping again.
At least 11.9.
So this part is going to be gone.
So we calculate the H2O needed.
It'll be at least 11.9, but it's going to be more than that because we can't only add enough oxygen to make the CO2. We also have to be making the water at the same time, right? The water is happening at the same time. So if we wanted to figure out grams of oxygen, we're just going to change the stoichiometry step. Now we're interested in oxygen. So we erase or start a new calculation, really, if you're on paper and not on a whiteboard. 2 moles of C2H2 makes 5 moles of oxygen burned or needed. So that's going to be arithmetic, yeah. 2.5 times 192. So something around 500. 480.
480.
480 even?
Yeah.
Okay, so for 3 sig figs, we'll do that. And that's moles, we want to get to grams. So we do another molecular weight.
1 mole is 32.
1 mole of O2 is 31.998. And we get
5,759, so 5,760.
5,000. That doesn't seem like enough.
Wait,
No, it's 15,000, so it's like 15,000.
15 point.
yeah, wait.
You might as well do one more sig fig since we're in the realm of actually doing calculations now.
15.4?
1, 4. So depending on what you round, it might have been a little bit different.
Yeah, 15.4.
Kilograms of O2, right?
And so I'm doing the kilograms to grams conversion in my head to save us room. But really, if we're in grams, your number that'll come out would be 1.54 times 10 to the 4 grams. And divide by 1,000 to get to kilograms.
We don't need kilograms.
We don't, but just because that's hard. It's hard to think intuitively about what scientific notation is. Sometimes it's helpful.
20.4.
So total mass of 20.4 on the left, which means the right-hand side should also add up to 20.4. If we did the same calculation for how much water can we make and added that to our kilograms of CO2 we could make, it should add up to 20.4 total. Right? That's where you get the conservation of mass, is in the total mass of products is equal to the total mass of reactants. All right, so a couple things that people do sometimes, or where people get confused, that I want to address before I just put you into the deep end. Just because there's a 5 in front of the oxygen does not affect the molecular mass. The molecular mass is per mole of O2. This says, in order for things to burn properly, I need 5 of them for every 2 molecules here. 2 separate things, right? So only this 2 matters when it comes to finding your molecular mass, because the molecular mass is not dependent on the reaction being balanced. The molecular mass is dependent on what the compound is, right? So the coefficients are only going to get used in our stoichiometry steps. No impact on molecular mass. There's one more other common thing. Oh, the number of molecules can change as well. So conservation of mass is all well and good. We have to have the same number of atoms before and after, but they can be arranged in different number of molecules. If we look at this, we have a total of 7 gas molecules on the left and 6 gas molecules on the right. That doesn't violate anything because their masses have to be the same. We're just putting together in different pieces. If I have 5 pounds of Legos, I can arrange them into 1,000 tiny things, or I can arrange them into 500 tiny things. It's still the same mass of Lego, still the same number of Lego pieces connected differently. All right. Couple more vocab things. I feel like we're in a good spot with these, right? This is mathematically, the math is very simple here. When I give you a piece of blank paper, it can be intimidating, but steps themselves are not that bad. So let's introduce a couple vocab terms. Some of that intimidating vocabulary that I think is part of why people get confused by this stuff. So theoretical yield is how much product could you make. A percent yield looks at how much product you actually made and compares to what you should have been able to make. If I had enough ingredients to make 24 hamburgers, but then at the end I used everything up and I only have 22 hamburgers, I didn't get 100% yield. There was some waste along the way. I dropped something, or some of my patties got too big, something like that, right? So if we have something like iron plus oxygen reacting to make iron oxide. If we start with 2.0 moles of iron and 1 mole of oxygen, what's our theoretical yield?
3 moles.
You sure?
No, wait, no, that would be wrong.
Do your math first, Jordan.
So the numbers aren't nice and clean, and we're not dealing with discrete objects like we were with the hamburgers. So you want to show your work. So figure out, okay, if I use all of my iron, how much product can I make? And then if I use all of my oxygen, how much product can I make? Theoretical yield is going to be whichever one's lower, right? So for every 4 moles of iron, I can make 2 moles of Fe2O3. Then we do the same calculation, but now from oxygen. If I have 1.0 mole of oxygen, and every 3 moles of oxygen makes 2 moles product. We have enough patties to make 100 moles, but only enough cheese to make 67 moles.
So the oxygen is the limiting reactant?
So that means that we're running out of oxygen first.
We've got vocabulary already.
Well, that's because I have the slides printed out.
Oh,
So we can say our theoretical, to give ourselves the vocab here, our theoretical yield would be 0.67 moles. Our limiting reactant is exactly what it sounds like. Limiting reactant means what's running out first, because that really dictates everything else, right? Go back to your cheeseburgers analogy. You run out of one thing, that stops the whole production line. So whatever can make the least product is going to be your limiting reactant.
And the other one's going to be the excess.
And if this is running out first,
We can only make 0.67 moles of Fe2O3.
you can only make 0.67 moles of iron oxide, iron 3 oxide, and that means we're going to have leftover iron. Right? If we run out of patties, but we still have 6 slices of bread left, that's excess.
Is that just the total minus whatever the limit it is?
Bingo. It goes, it's a really, the terms, when you understand the terms, the math behind them is really easy. You want to know how much excess you have, you figure out how many moles you started with, and you figure out how many moles you get used up.
So you take this number and go back to iron and just subtract?
Basically. So we'd say our limiting reactant, if I ask what the limiting reactant is, it's not a number. It's going to be whatever runs out first. So it's always just going to be identity of a compound. So our limiting reactant is oxygen.
So if we take the number from where oxygen goes to iron oxide, go back to iron, that'll give us a smaller number than 2. Subtract, that'll give us the excess.
You can pick and choose wherever you want to start for this, because it's doing 2 different sides of a square to get to the same place.
Okay.
Right? Since we already have 1 mole, since we know oxygen's what's running out, oxygen's what's controlling how many times the reaction can happen, we can say, okay, well, if I use up all of my moles of oxygen, for every 3 moles of O2, that's 4 moles iron used.
And that's 1 step.
And then it's only 1 step. So
Whoa.
0.67 excess.
So if we want to know how much iron is left over, we look at what did we start with, and we look at how much did we use. How much we started with is either given, or you get to it from mass of iron at the beginning. How much is used, you take whatever's running out first, and you do a stoichiometry step. So that allows us to say, okay, well, if I had 2 moles of iron initially, and I used 1.3 moles, how much is left?
0.7 moles.
Just do the math, right? So it's having these qualitative terms on there can be really helpful to see the logic behind this. Because again, it's really easy when I do it in cheeseburger language, right? When I put it in moles, it's harder to see what's going on just because it's a more abstract concept. I joke like I don't understand why it's hard. I know why it's hard. Chemicals are abstract. You don't know what a chemical looks like. You've never touched one in molecular form, right? So I get why it's hard, but just remember that the math should be easy. There's nothing complicated about the math. All the steps are simple. And they should make logical sense. So the amount that's left over, the 0.7 moles iron left, or excess.
We started with 2 moles, though.
We started with 2 moles,
And we got 1.3.
and we lost 1.3. All right, so once you understand the vocabulary, you kind of, everybody when I get to this part always just says, well, just teach me the procedure. Let me memorize the procedure that I can go crank through the numbers every time. It's not a procedure, it's understanding, are you making something, are you losing something? And sort of putting the logic to it when it comes to the language of the word problems, which is not all that comforting. It's comforting to have a procedure you can follow every time. I get that.
That's not the world we live in.
But that's not the world we live in. And it's cheeseburgers, guys. If you have 20 slices of bread and you make 12 cheeseburgers, how many slices of bread are left? 8. You guys can all do that in your head when it's bread. It's the same thing.
We're Americans.
Everybody likes bread. I think that crosses international borders.
Yeah, it only makes sense to Americans if there's food involved.
All right. Actually, let me put that back up.
You stopped at the same.
Yeah. No, I knew where I was headed with that. So we had our theoretical yield was 0.67 moles, right? If we actually do this reaction and we measure how much product we can get, and we actually say, okay, our actual yield is 0.50 moles. Because sometimes when you do a reaction, not everything goes perfectly. Sometimes reactions don't go all the way to completion just because there's not that much difference in stability between products and reactants. Sometimes the products are less stable than the reactants, and so you might only get like 10% yield. We're making the assumption with the theoretical yield that this goes 100% as far as it can towards the products. In our cheeseburger analogy, we're assuming we need to make as many cheeseburgers as possible. In the real world, you might have enough ingredients to make 16 cheeseburgers, but you only have 8 people that want a cheeseburger. That doesn't change the theoretical yield, it just changes how much you actually are going to make. Right, so if our actual yield I went to correct that and then rewrote it the same way. Oh, that looks worse. So I went to correct it and wrote it the exact same way because it was already right.
75% yield.
So percent yield is you take what you actually got, divide by what you should have got. Ignore my grammar on this because I can't use it properly when it comes to describing this.
74.6% yield.
So percent yield, and this is on your equation sheet. Percent is always part divided by the total. If we're talking about percent yield, it's what you actually get divided by the theoretical times 100, which comes out to be 75% in this case, right?
Yeah.
Takes some good numbers.
Like 6 days.
Right, so key vocab verbs we have added. theoretical yield, limiting reactant, excess reactant, percent yield, and I think that's the bulk of what I will ask. So what I will do on some of these problems, this will be some of your in-class assignment for next week. It will be done out of class. I will give you a reaction. I'll give you a starting amount and an actual yield and say, what's your theoretical yield? What's your limiting reactant? How much excess is left over? And what's your percent yield?
Will you give us a balanced equation or not?
No. Maybe sometimes, but you always want to double check it. Don't trust it just because I gave it to you.
If there's a coefficient in it, when you give it to us, can we assume that it is balanced?
Only if you want to assume that I did it properly, which is not
That would
always a
be
good
on-
assumption.
That would be on you guys.
Generally speaking, but it's not a bad idea to double check because you can wind up with answers that don't make sense if it's not balanced.
Okay.
All right, good work this week. That was slow, but also a very big lecture in terms of the number of different ways I can ask word problems now.
So Sean, for some of these examples that you have in your notes, underneath the product side, you're showing grams, but it says actual.